Hello everyone. This is the first of a series of videos dedicated to acid-base chemistry. In these videos, I will be covering quite some key concepts related to acid-base chemistry. We will be looking at what acids and bases are, so the definitions, and we will be looking at how we can predict if a substance will behave as an acid or as a base when dissolving water. We'll be looking at the concept of pH. What is pH? What we care about pH? Why we define the pH scale and how we use it? And also we'll perform some simple calculations, how to calculate the pH of acids and bases. We'll be looking at the concept of neutralization reactions, and that's quite useful. This part will be quite useful for any work that you have to do in the lab that involves a neutralization reaction. So what neutralizations are, how they work, and how we can perform calculations related to neutralization reactions. And finally, we will be looking at something called buffer solutions. So what are buffer solutions? Why we care about buffer solutions? Why we use buffer solutions? Both you humans and also nature. They are widely represented in natural and biological systems. And we will be looking at an equation called the Henderson-Hasselbalch equation that allows us to perform some simple calculations related to buffer solutions. I've divided the topic in several videos, hopefully to make the different concepts easier to follow and the whole topic easier to follow. And if you have any questions, just let me know and we can organize a tutorial. Water is a solvent of life. 3/4 of our world is covering water. Cells contain 80–90% of water. The cytoplasm cells are water-based environments in which biochemical reactions occur. And the chemical environment of cells is highly regulated. So the cells keep concentrations of all sorts of compounds within certain limits that life can tolerate, that the cells can tolerate. And a lot of effort goes into regulating those environments. And a very important two crucial elements to stabilize those water-based environments are acids and bases. And biological systems play a lot with the concentration of acids and the concentration of bases inside the cells, in the chemical processes, to keep the environment, the biological environment stable. So what is an acid and what is a base? Well, there are several different theories. I'm going to be covering in these videos 3 of them. And they came like in chronological order, and they were mostly based on what we knew were acids and bases at the time. So we have one from the late 19th century, the Arrhenius theory by the Swedish chemist, and then the 2 from the 20th century. Bronsted was Danish, and Lowry was a chemist, a British chemist, and also finally Lewis theory, which is the one that probably encompasses, it's the most encompassing of all of them, because we will see later any substance can be defined as an acid or as a base using the Lewis theory. So let's start with an acid is. Well, according to Arrhenius, an acid is a hydrogen-containing compound, so a compound that has hydrogen, that when you dissolve it in water, produces the hydrogen ion, the ion H+. And what are examples of acids? Well, any compound you can think of that has the word acid in its name. So hydrochloric acid, sulfuric acid, nitric acid that are mentioned in this slide, but phosphoric acid, formic acid, acetic acid. All those compounds have hydrogens, and some of those hydrogens, or all of them in some cases, like in the case of the compounds I've got in the slide, can be, when the compound reacts with water, can release hydrogen in the form of a cation, the hydrogen ion. Bronsted-Lowry theory. Bronsted-Lowry defined acid, and we'll see later base, is not what the substance had, but what the substance could do. So they define acids as a substance that can donate hydrogen ions to another substance. And look that I've used the word proton, and more about why I use the word proton in a later slide. So Arrhenius theory is a compound that has hydrogen that, when dissolving water, liberates the hydrogen as a hydrogen ion, an H+ cation. Bronsted-Lowry theory, any substance that can, when dissolving in another substance, or when dissolving water, can donate hydrogen ions, H plus ions, to another substance. Lewis theory does not look at hydrogens at all. Lewis theory looks at electrons, and you're an acid or a base depending on if you can accept electrons or donate electrons. And we will look at later on why that's a very powerful theory. So Lewis defined an acid as a substance that can accept electrons from another substance. So any substance that has the capacity of accepting electrons can be defined as a Lewis acid. So yes, the compound H plus, the cation H plus, the hydrogen ion, because it has a positive charge, so it can accept electrons, but also any metal cation you can think of, sodium plus, calcium 2 plus, etc., can be defined as an acid because they have positive charges, so they can accept electrons to compensate those positive charges. That would be their natural behavior. Bases. What is a base? Again, the 3D theories differ slightly how they define base, mostly because they were defining bases as what they knew at the time. So when suddenly the theory, Arrhenius theory was the first theory that came along in the 19th century, and he defined base as a compound that contains the hydroxide entity, which is the oxygen and the hydrogen attached to each other, so this OH fragment, and when you dissolve it in water, releases that OH fragment, but as an anion, OH minus, and he called that a hydroxide ion or hydroxide anion. So what's an example of an Arrhenius base? Potassium hydroxide, sodium hydroxide, calcium hydroxide, aluminium hydroxide. Anything that has the hydroxide word in the name will be a base because it has that OH fragment that when dissolving water the compound can generate that OH as an anion, the hydroxide anion. That was a bit limiting because there were compounds known at the time or later on, for example, the compound ammonia, NH3, that has hydrogens. It does not have OHs, but does behave as a base. Does behave as a base. It is a base. And Bronsted-Lowry changed the definition of base, looking not what the compound had, but what the compound could do. So a base, according to Bronsted-Lowry, is a substance that can accept hydrogen ions from another substance, an acid. So an acid donates hydrogen ions, a base accepts hydrogen ions. And most of the exercises, or if not all of the exercises we're going to do throughout this topic, are based on these two definitions. If you're an acid, you donate hydrogen ions. If you're a base, you accept those hydrogen ions. And suddenly compounds like ammonia and NH3 became, were car-carrying bases that Arrhenius could not explain, because ammonia can accept, and we will look at, ammonia does accept hydrogen ions from another substance. And finally, the Lewis theory. Lewis theory again doesn't look at hydrogens and OHs or whatever. It looks at electrons, whether you can donate electrons or you can accept electrons. So according to Lewis, a base is a substance that can donate electrons to another substance that can accept them. That's the acid. And so any substance that you can think of can be defined as an acid or a base according to Lewis, because they either have electrons that can donate. If you think of the ammonia, the compound ammonia, NH3, that nitrogen has 2 electrons sitting in the nitrogen, and that can that can be donated. Or the compound H2O in the oxygen, if you remember the V shape of the oxygen, and the oxygen in the middle has electron pairs that are not being shared by the hydrogens. Those electrons can be donated to other substances. So that makes them bases. So Lewis theory is quite powerful because it explains all the other compounds that Arrhenius and Bronsted-Lowry explain. But apart from that, it means that any compound you can think of can be defined as an acid or a base because it will have electrons. So it will have a tendency to donate electrons or a tendency to accept electrons. For these videos, the most useful definition for us, and the one that we typically use in biological system and in water chemistry, is the Bronsted-Lowry definition. So an acid donates hydrogen ions, a base accepts hydrogen ions. So if we look at this slide, there's a couple of examples of bases that would fit the bill in different theories. So the first one, sodium hydroxide, would work in the Arrhenius definition. it's a base because you have the sodium and the OH, and that's an ionic compound. The OH is the oxygen and the hydrogen are bonded by a covalent bond, so they're sharing bonds. They're sharing electrons, sorry. The sodium and the OH are an ionic compound, make an ionic compound because the sodium has a positive charge, sodium plus, and the OH is negatively charged, OH minus. So when you dissolve it in water, the ions separate, and you have the sodium ions that you don't particularly care about, and the OH minus, the hydroxide anions, and you care about them because that's what is going to they're going to behave. It's going to make sodium hydroxide behave as a base. So all Arrhenius bases are ionic compounds because they will liberate that OH minus anion. Brewster-Lowry definition or Lewis definition look at, okay, not what you have, but you can do. So in the case of Brewster-Lowry, a base is a compound that can accept hydrogen ions from another substance. And here the example of ammonia, you have the 2 electrons sitting on top of the nitrogen. Those are electrons that belong to the nitrogen. They are not involved in the bonds with the hydrogens, and they are there, and they can be used, to react, to interact with these hydrogen ions if it's in solution. So the ammonia, the molecule of NH3, has this ability of accepting a hydrogen ion and become the NH4 plus ion. Is called ammonium ion. The same happens with water, for example. If you think of how the molecule of water looks like, it has electronic pairs sitting on the oxygen. They are not involved. They are there, they are in the outer shell, but they are not involved in the bonds with the hydrogen. So, again, if there is a hydrogen ion in the medium, the oxygen can capture those 2 electrons from the oxygen can capture one hydrogen ion, and you make this compound, the ionium ion, which has a positive charge, the hydronium ion, which we normally call also hydrogen ion. A little bit about more about proton, hydrogen ion, and hydronium ion in a later slide. Very briefly, because we're not going to use it for these videos, but Lewis theory. Lewis theory is the most powerful of all the theories, of the 3 theories, because it looks at electrons, and you can do what you can do with electrons. If you can accept it, you can donate them. And all substances that you can think of, they all have electrons. Doesn't matter if the compound, if it's a compound or a single element, if it's an ionic or a covalent compound, it will have electrons. So it will have either a tendency to donate them or accept them. They might not be very good, but they can do it. So using the Lewis theory, any compound you can think of can be classified as an acid or as a base. If you have the tendency to accept electrons, then you behave like an acid. So these ones, in Lewis theory, are acids. Because, well, they have a positive charge. So hydrogen ion, yes, is an acid, but a metal cation is also an acid. So sodium plus, or chromium 3 plus, or copper 2 plus, any positive ion, any cation, any metallic ion, will have a certain acidic tendency, better or worse depending on how good they are. But they can behave like acids. And all these ones here, in Lewis theory, are classified as a base. They are called Lewis bases. And they are substances that have electrons that can be donated. And they have electrons either because they have non-bonding electrons, so for example, in the case of the oxygen in the water and the nitrogen in the ammonia, so those are non-bonding electrons, they are not involved in the bonds, so they can be donated to an acid, but also a substance like the Cl-, like an anion, a chloride anion, a bromine anion, a sulfate anion, something that has negative charges, because again, those are electrons that can be donated. Those can also be defined as Lewis bases. So it's worth keeping that in mind, just because it's a very powerful theory which does not have the limitation of the hydrogen ion, as long as a substance has electrons, and they all have, can be defined as an acid or a base. But for the purpose of these videos, the most useful definition, the one that we're going to be using all the time, is the Brewster-Lowry definition. So if you're an acid, you donate hydrogen ions. If you're a base, you accept hydrogen ions. So I'm going to ask you to stop the video one moment and define the reagent or the substance in the left-hand side of this equation as an acid or as a base, according to, well, let's say Browser-Lowry definition. Stop the video now, please. I hope you stop the video and had a go at the exercises. Okay, if I look at the substance of the equation A, bromidric acid, HBr, I can see when I dissolve it, or when it dissolves in water, it releases hydrogen ions and the bromide anion. So that's a substance that has released hydrogen ions, so that this can be defined as an acid. So HBr is an acid. If I go to equation B, Cn minus is a cyanide anion, and if I look at the reaction, it's a cyanide anion plus one hydrogen ion to give cyanidric acid. So, well, it's clear in the equation that Cn minus, the cyanide anion, has accepted a hydrogen ion, so it has behaved as a base. I don't know what you did with the water. That's an interesting question. Is the water an acid and a base? Well, now, on one hand, it has liberated a hydrogen ion, okay, fair enough. And the other one, it has liberated an OH minus, a hydroxide. So I would define it as an Arrhenius base. So is it an acid or is it a base? Well, I'm going to park this discussion for a few slides, and we'll pick that up later. But I would be curious to see what you decided it was, if it was an acid or a base. And finally, let's look at equation D. That's the equation of ammonia, NH3. So ammonia reacts with a hydrogen ion to produce the ammonium anion, the ammonium cation, sorry, NH4+. So NH3, the compound ammonia, is a base.